Alrighty, so today we're going to be talking about section 6.8, analyzing graphs of polynomial functions. So to start off, we'll be relating zeros, factors, solutions, and intercepts. We did a little bit of this yesterday, but we are going to continue this because it'll help us as we sketch our graphs and as we analyze our graphs of our polynomial functions. Okay, so as we start off with our zero, that's when k is a zero of the polynomial function f. So all that is saying is that our x value, that is going to equal k. Okay? For a factor, that is when x minus k is a factor of the polynomial function f of x. So to go from this step of having that as a zero to a factor, all we would do is subtract k from both sides. So that would give us our x minus k, and that equals 0, and that's what makes this a factor. For our solution, k is a solution of the polynomial equation f of x equals 0, and all that is saying is f of x. That's a nice way of writing y equals 0. And something about our solution is this can be real or imaginary. Okay, and if it's imaginary, we're not going to see it on our graph. And for our x-intercept, that's if k is a real number, then k is an x-intercept of the graph of the polynomial function. Now, since k must be a real number, it can be seen on our graph, okay? So it's one difference between our x-intercept and our solution, because our solutions don't always have to show up on our graph because they could be imaginary numbers, which we wouldn't see on our graph. Okay, so as we scroll down and we're looking at this first example, it says sketch a graph of f of x equals 2x cubed minus 5x plus 4. Okay, so if we're starting off with that, let's put this into our calculator and see what we can get. Alright, so I just made the screen a little bigger so we can see the calculator. So if we go to sketch our graph, let's put it into our calculator first. So we have 2x cubed minus 5x plus 4. Make sure that's a minus sign and not a negative sign. When we hit graph, first I'm going to make sure it's in standard. So this is what our graph should look like. So if we graph this on our axes over here, it doesn't have to be perfect, but just do your best. So it's starting low and it's going up. I don't like that. Starting low, increasing, then it switches and it goes back up. I'm just going to redo that. There we go. Something like that. Okay. So, looking at this graph, we need to think about our important points that we can find right away. So, looking at this, there is a couple ones that are super easy to find right away. And we should know this from our previous chapters of what we've been doing. So looking at this, we could figure out what this point right here is. That's our x-intercept. So let's find what our x-intercept is on our graph. So to find this, that's the point when our y equals 0. Okay, so when we are looking for this, there's a function in our calculator to help us find our 0. So if we go to second trace, we're going to look at for our 0 function. So if we hit the second option, now left bound, so that means we're going to go all the way to the left of our 0, so until it's negative. So over here we hit enter, then we go to the right, so it's positive, so our y is positive. We hit enter, and then to guess, we just move a little bit closer to the 0, so I just moved 1 to the left, hit enter, and then we get our point of negative 1.89 comma 0. Okay, so that's our x-intercept. Okay, another point that we can find on this graph is our y-intercept. That's also an easy one to find. to find our y-intercept, that's when our x equals 0. Okay, so looking at our graph, all we have to do is if we hit trace, if we can put in whatever x value we want, and it'll tell us our y value. So trace, we want to find out when x is 0. If we hit enter, it'll tell us what our y value is. Oh, and it's 4. So when our x is 0, our y is going to be 4. And another way that we could have figured that out is just looking at our equation. If we plugged in 0 for x, that would get rid of your 2x cubed and your negative 5x, so you're just left with your 4. Another way to find your y-intercept. Sometimes it's that easy, other times it's a little bit more complicated. So, so far, that's the only thing that we've really talked about of finding on our graph. But there are some other important parts that we could find. Looking at our graph, we have these things here called turning points, okay? So that's one of the important things that we can find on our graph. And turning points, as obvious as it is, it's where our graph changes direction. And it helps us describe the shape of the graph. Okay, so then for this case, we have a turning point here and a turning point here. We have 2 turning points for this graph. And what we call these is, we'll call them a local minimum and a local maximum. So if you're looking at these 2 points, which one's going to be our local minimum? This one, because it's our lower point, so that would be our local min. And local max, this would be our local max because it's higher. To define these 2 words, our local min, that's going to be our point lower than all nearby points. Okay, so local min, that's lower than all the points that surround it. Okay, that's where it turns direction. And a thing to note, this is not necessarily the absolute min. Now what that is, the absolute min, that's the absolute lowest point of the whole entire graph. As you can see, it goes down to negative infinity towards the left of our graph. So this point here is not the absolute min. Now we'll talk about later more examples where you might see an absolute min, but in this case it doesn't have to be an absolute min. And likewise, a local max, that's our point higher than all nearby points. And likewise, it doesn't necessarily it's not necessarily the absolute max, because in the same way this goes off to infinity, it gets higher and higher, so this point is just our local max. Okay, something to note about about this is that every polynomial has at most, underline that, n minus 1 turning points. Okay, so in this case, if we're looking at this polynomial here, it has 2x cubed minus 5x plus 4. So our n minus 1, that's talking about our degree. Our degree of our function here is 3, so this graph is going to have at most 2 turning points. And if we're looking, it has 1 turning point here, 1 turning point here. So it does have 2 turning points. So that's the most it can have, and that's the amount that it has. So That is true of all of our polynomials, okay? So every polynomial has at most n minus 1 turning points, okay? Now, as we move on, for each of these graphs, we want to sketch the graph, describe the end behavior, find the x-intercepts, and find the local min and local max. Okay, sometimes I might ask you to find your y-intercept like we did in the first problem, but not always, so make sure you know how to do that as well. So for this one, sketch the graph. Let's put that into our calculator. So we clear that out. And let's put this in x to the 4th plus 2x cubed minus 6x squared minus 12x 12x minus 6. So let's graph that, see what that looks like. Ooh, I'm missing a bottom part of the graph, so what I'm going to do is make my y min a little bit smaller so that way I can see. I'm just going to guess, maybe do negative 30. So that way I could see it. This is more of like a guess and check. You don't really know how low you'll have to go, so you may have started with negative 20 and then you may have had to go a little bit lower. But make sure you can see the whole graph in your picture here. So let's sketch this. Starts high, goes low, increases, then decreases. I don't like that. It drops a little further. Okay, that's fine. So this is our graph, so this is our sketch. And as we go, let's describe our end behavior. That's just a review from yesterday. So if we remember, that's saying if as f of x, we're saying that either has to be going to positive infinity as our x goes to positive infinity. So we're looking as x goes to positive infinity, what's happening to our y? Oh, that's also increasing. So going to positive infinity. And then for a second part, as x approaches negative infinity, what's happening to our graph? Oh, that's also going to positive infinity. So that's our end behavior. To find c, that's our x-intercepts. So in the same way as we did in our last graph, we need to look, we want to find these points here. So to do that, again, we go to second, trace, and we're going to use our 0 function, so that's our second option here. And I'm going to find the 0 that's more to the left first. So left bound, so that just means to the left of the 0. So that means I'm looking for the positive somewhere up here. So, okay, my y is positive. I can hit enter. Then I'm going to go down a little bit. Oh, okay, it's on the other side of my 0, so I can hit enter. And then guess I'm just going to move my cursor closer to the 0 point, hit enter again. Oh, and that gives me the point of negative 2.89 comma 0. This 1e to negative 12th, that is just saying 0. Okay, so that's negative 2.89 comma 0. And to find this other point, we do the same thing. Second trace, second option. Now let's move all the way over closer to the other 0. But we still want it to be to the left of the 0, so we'll still be in this region here. So stopping there is fine. Hit enter. And right bound, it has to be positive to the right of the 0. So mine's up at 36. That's fine. Hit enter. Then we're going to have to go a little bit closer to the 0. Hit enter. And that gives us the point of 2.55 comma 0. Negative 8e to the negative 12th, that's negative 8 times 10 to the negative 12th, which is 0. So these are our two x-intercepts that we have. Okay, and like I said before, you should know how to find your y-intercept if asked, but in this case, didn't ask you. Now what I need you to do is go on to the part 2 of this video, okay?